So that's a defining property. Namely, whenever you have an operator with such a property, then this operator is called a projection. So P is a projection. So also we have seen last time that, well, there's this basic example of an orthogonal projection, right? So P of V is just, if you just take the usual, the classical, the well-known orthogonal projection that you have been dealing with in the first year linear algebra, and that's a particular example of such a linear operator. So it's a projection, is an example of such P. These two linear subspaces, V1 and V2, are linear subspaces in some vector space V. Then what we can do, well, we can try to add them in a way that V1 and V2, they sort of do not intersect. Well, rather, it's better to say that they intersect along the zero vector only, right? So if we know that V is a sum of V1, V2, meaning that any vector from V can be written as a sum of a vector from V1 and a vector from V2, and at the same time we know that and the intersection is just zero, so the smallest possible intersection, well then, well, this V is called the direct sum, is a direct sum of V1 and V2. Okay. Well, produce a couple of examples. Well, actually last time we also introduced an example of R2, well, several examples of a direct sums, right? It's like, for instance, you can add the coordinate lines, yes, on the plane. So the R2 is just a direct sum of coordinate lines. Also, we can look at it like as a direct sum of, say, one of the coordinate lines, say, and the diagonal line, if you wish, yeah, and so on. There are plenty of other examples. Well, let me now provide another example of a direct sum concept definition. So yes, so suppose that V1 and V2 are vector spaces, so be vector spaces over the field F, or if you wish, with the coefficients from the field F. Now consider the following set. Well, we all know that given two sets, we can form its product, right? Its Cartesian product, the so-called Cartesian product. So basically it's a new set which consists of pairs of elements. The first coordinate is taken from the first set and the second coordinate from the second set. Yeah? So that's the so-called Cartesian product. So consider this set. Now, well, we know that V1 and V2 are vector spaces. However, we don't know yet whether V is a vector space or not. We only have this V, we only have defined this V as a set, right? And in order for V to be a vector space, in addition to the fact that it is just a set, well, vector space V2. Oh yeah, good. Okay, right. So let me repeat it. It's always useful to repeat. So, right. So what we would like to do, again, we would like to introduce an important example of a direct sum. And that's, but since this is an important example, I would like really to sort of to use a separate name for this. And that's why I say definition. So what we are given two vector spaces, V1 and V2. And what do we do? Well, let's look at the Cartesian product of these two vector spaces as sets. So we get a new set, V. okay? And then what I'm going to do, I'm going to introduce the addition of vectors and the scalar multiplication on this set V. And how do I do this? Well, okay, so given any two vectors like this, V1 and U1 and V2 and U2, well, what is just define, so define plus on V to be, well, using the following rule. So what do we do? Well, if we say have, say V1 and V2, and we would like to add this vector to the U1 and U2, well, the result will be given just by adding the respective coordinates in these pairs, namely, well, just set it. So the sum is set to be just the sum of these coordinates, the first coordinates and the second coordinates. Again, those coordinates here, they are not numbers, they're vectors, right? So be careful. So those are just vectors, okay? So this gives us the sum. So whenever I have one pair of elements and I would like to add it to another pair of elements, I'll get another, well, a new pair of elements, which is just this one. Okay. Now, of course, one can check that this operation satisfies all the necessary operations for, well, for the vector addition, right? So it's commutative, it's associative, it has zero. So what's a zero, by the way? The zero is just 0, 0, right? And so on. So you just check that all the operations for the vector additions, for the vector addition are satisfied. Well, we can also define the scalar multiple as following. So whenever I have, say, scalar C from my field F, and I would like to multiply a given pair of vectors, say V1, V2, by that scalar, what's the result? Well, the result is what one expects. What do we do? We just multiply, well, we just multiply it coordinate-wise. So we just set it to be C times V1, comma C times V2. Where this dot here, where these dots here are just the usual, the given scalar multiplications in the vector space V1 and V2. Okay, so in this way, we get two operations. So on this set V, we obtain two operations. One is plus, another one is multiplication by scalar. And one can easily check, just look at the list of properties for the vector addition and the scalar multiplication, that this gives an example of a vector space. So V is a vector space. By the way, put it as a definition, because I need a name for this example. I would like to introduce a name. So again, I mean, if we define our V in this way, just by taking the Cartesian product of two vector spaces, and these operations plus multiplication by scalar in this particular way, then such a V is a vector space called the direct sum of V1 and V2. And maybe it would be better, it would be natural to stress what kind of direct sum. Let's put it in this way. We call the, well, let's put it in this way, say standard direct sum of V1 and V2. Because there are many other direct sums, right? So to stress that this V precisely is obtained just by using this Cartesian product and these operations, we call it a standard direct sum. Okay, but well, still, okay, this V is a vector space, that's okay. But we still need to check that this is a direct sum, right? We still need to apply the previous definition to see whether it's actual direct sum. Yeah? It's a standard direct sum, but why it's a not direct sum? Okay, so let's check it. So it's a property. So let's state it as a lemma. So it's indeed lemma 5.6 in the lecture notes. So the set, okay, so let me say this. So given V, which is V1 plus V, sorry, times V2 as before, we have V is indeed a direct sum of V1 plus V2. So indeed this symbol in this particular example can be replaced just by this direct sum symbol. Yeah, so just the same. Okay, so well, maybe I would like to be a little bit more precise where what is V1, because V1 has to be a subspace. You remember in the definition of the direct sum, we require both V1 and V2 be linear subspaces of V. But in this case, it's clear what kind of subspaces are there. Well, we just keep one of the coordinates and set another coordinate to be 0. This will give us the subspace. So let me write it. So in this case, what is V1? V1 is just, we keep the first coordinate, comma 0. So that's from V, such that, right? So V1 is from V1. And V2 we can identify also with the second coordinate. So it's the same V2. And V2 from V2. So are viewed as linear subspaces of V. Okay. Again, I mean, of course, whenever we have a Cartesian product, we can just look at the first component, which is V1, right? So we can just put 0 at the second position. So it's the same V1. And also we can look at the second component, which is V2. And again, we just put 0 at the first position. And that's the same V2. And that's why I just put equality signs here. Okay, so, right. So let me justify this proof. And we just, what do? We just follow the definition. We just follow the definition of the direct sum, right? So we'd like to show that V is a direct sum here. And again, well, we just need to verify two properties, right? So first is that any vector V from V can be written as the sum of two vectors. So let's put it this way, V1 plus V2, where V1 is from V1 and V2 is from V2. And second property, let me just remind you, we need to verify that V1 intersect V2 is 0. It's a 0 subspace. It consists of only 0. Yeah? Okay, so what about the first one? Let me put 1 and 2. What about the first one? How do we show this? Well, okay, so suppose that we are given a vector from, V, right? Remember that V was V1 times V2, meaning that this V is just a pair of vectors, right? So V is just, say, V1 and V2. That's a definition of the product of two sets, where this is taken from the first set and the second coordinate is taken from the second set, right? And now, well, what do? We do this standard trick from the first year linear algebra. We just expand this expression. We just separate the coordinates. Namely, we just write it like this. So V1, 0 plus 0, V2. Well, of course, if we add them, if we add these two vectors using our addition, using this formula, yeah, look, I mean, there's a 0 here and 0 there. What do we get? Well, we get exactly we get exactly what we want. We get exactly V1, comma V2. And look, I mean, this is precisely V1, right? This is our V1 here. And this vector is taken from V2. So it's precisely taken from this V2 here. So meaning that again, I mean, we can just write down any vector as a sum of vectors from V1 and V2. So that's okay. So the first condition is verified. Now, what about the second one? Well, for the second, it's also okay. So let's look at the intersection. So what's this? Well, let's just look at this description of those vector spaces, of those subspaces. What do we see? Well, we see that what's the intersection? Well, the intersection is just a vector which has the second coordinate 0, right? The second coordinate is 0. And the first coordinate also must be 0 because it's and, right? It's an intersection. So it must be both of this form and of this form. So it means that, well, there's no way, right? This has to be just this. And this is precisely the 0 vector in our product space. Yes? So we are finished because, well, we just checked both conditions. So meaning that V is really a direct sum of two such subspaces. Most of you are pretty familiar with this one. Say, well, let's just look at R, just the set of real numbers with the usual addition and multiplication. So it's our field F, right? And what can we do? Well, we can just take its product with itself as many times as we wish, right? We can just take R, well, let's just take this, R times star, right? And of course, this is denoted as R2, right? That's what we all remember from the first year linear algebra, because each point here, each element of this set is precisely this X, comma Y. It's a point on the plane, right? Because this is a plane here. And it consists of all points like this, from the first coordinate and from the second coordinate. Yeah. Well, of course, we can do a little bit more. Well, we can, of course, do this. Well, we just take, say, R2, and well, we can add another copy of R to this. Why not? And in this way, of course, we'll get R3. Or if you wish, I can also do it like I can expand it and do it just by taking the product of 3 copies of R, right? And again, we all know that this is just a 3-dimensional space, right? And each element of this 3-dimensional space, well, it's just a triple of numbers. We all remember this, right? Now, by the very definition of the Cartesian product of 2 sets, that's what? This must consist of 2 pairs, x1, y1. It's a pair of pairs, right? Yes, exactly, it's R4. So, and then I can just put it like this, yes? And then pair of pairs, yes? Because that's a first, so this vector is the first coordinate here, right? And this vector is first coordinate there. But of course, if I write a pair of pairs, then it's just the same as to write x1, y1, x2, y2. Of course, right? Because the orders, well, one has to keep the right order here, but that's eventually just a tuple of 4 elements, 4 numbers, right? So x1, y1, x2, y2, they're all numbers. Okay, so that's my v1. This is my v2. Yes, this is my small v1. This is my small v2, right? And of course, this is just a vector in v1, and this is just a vector in v2. Yes, and then, well, clearly v1 is the first coordinate in this pair, right? And v2 is the second coordinate of this large pair, right? Okay. Yeah, so, right, as you see, you can basically form a lot of examples of products, right? And in this way, we can get a general, what is Rn? Well, Rn is just a product of R with itself, well, precisely n times, n times. And this is a vector space using, well, we can define it, the standard addition and multiplication by the scalar. Standard in the sense that as we did before, so it's a coordinate-wise addition and coordinate-wise scalar multiplication. And well, from the previous fact that we have justified, what we can also say is that, well, look, I mean, this is the same as also the direct sum of R and R. Yes. And well, indeed, this is precisely the example where, what's this? This is just the first coordinate, and this is the second coordinate in R2. And that's precisely the, so indeed here we just come back to this example of the previous lecture. So this is OX and this is OY. Yeah, this is the first coordinate line and the second, I mean, that's just coordinate lines. And so on. I mean, for R3, we can also say that this is the same as R plus R plus R, several many times, or it's the same as R2 plus R, doesn't matter. Yeah, so whenever we see this cross, we can always replace it just by this concept of a direct sum that we just introduced. Yeah. And so on. I mean, well, we can also write it as a plus R precisely n times. So Rn indeed can be viewed also as a direct sum of n copies of this one-dimensional space R. Okay. Indeed, maybe before going to the next slide, I would like to mention that this direct sum, this concept of a direct sum can be viewed as sort of, I mean, if you have two vector spaces, you can sort of add them, right? So it's kind of addition for vector spaces. So it's sort of abstract addition. So here you add, instead of numbers, you add vector spaces. It's kind of a little bit weird, but that's what it is. And well, you can clearly check that this operation, this kind of abstract sum of vector spaces, satisfies the standard properties of the addition, namely it's commutative, it's associative, right? And it also has the identity, the additive identity, right? Because look, I mean, if I take the zero space and add it to anything, I get this V, yeah, and so on. So that's a nice operation between vector spaces. Okay, so there's a lemma. So suppose we have a projection. So we all now know that it's a linear operator, right? From the vector space V, from some vector space V to itself. So it's a linear transformation, which satisfies this nice condition. P composed with P is P. So let P be a projection. Right? So one may think about, one can look at, say, the kernel of this linear transformation. I hope everyone remembers what the kernel is. Well, let me just remind you, that's just the preimage of zero. So it's all those vectors that go to zero. And at the same time, one can look also at the image of this linear transformation. So again, it just consists of all vectors, say W from V, such that P of V is W for some V. So it's an image, it's a range, right? And we all know that those are subspaces, right? Remember that this is a subspace of V, and also the image is a subspace. Of V. Okay. And so, so we have two subspaces inside our vector space. And that the claim is, and that's what we would like to justify, to prove, is that indeed our V, our total vector space V, is a direct sum, is always a direct sum of the kernel and the image. Okay, so that's a pretty important fact. And yet you see that the direct sums appear naturally out of projections, right? And indeed, we will see later on that any direct sum would correspond to some projections. So it's the other way around. The opposite way also works, right? As you remember that whenever, so first condition, maybe I put one, is that V is just a sum, meaning that we can express any vector from V. Just pick up any vector from V, then we should be able to express it like, say, V1 plus V2. Maybe just to be consistent with the previous notation, I would like to set this to be V1. And okay, let me put it here. This is my V1 and this is my V2. Yes. Okay. So yeah, so first we want to understand why any vector from our capital V can be expressed as a sum of vectors V1 and V2. And second, just, well, we need to understand why the kernel of P intersect with the image of P is 0. So these two things we would like to understand why this is happening. Okay. Now I'm going to justify the first one. So what do? I just define V1 to be this expression. So it's a small trick. So just we take V minus, well, we just apply P to this vector V. And define V2 to be just, well, we just take it as P of V. Then what do we see? Well, we see that clearly V is just V minus P of V plus P of V, right? And this is exactly V. That's fine, yeah? That's okay. But on the other side, this is V1 and this is V2. Why? Because look, I mean, V2, it's where? Where does it sit? Well, it's an image of V, right? We apply our linear transformation to the vector. So this definitely sits inside the image of our P by the very definition. If you just look at the image here, this one, so that's clearly the case, right? So, okay. Well, now, well, we claim that this guy isn't, well, indeed sits in the kernel. Why is it so? Well, let's just check it. Let's just apply P to our vector V1. Well, that's what? It's just P applied to V minus P of V, right? I just substitute. So that's my V1 here. And then, well, the P is a linear transformation. So I can open the brackets like in the standard way. So just P of V, just open this, minus P applied to P of V, right? So this is just this P of this. And then, well, what's this? This is just P of V minus, and then look, P was chosen to be a projection. So it satisfies P composed with P is P itself. And that's precisely what we have here. So it's P composed with P. So meaning that here just have the usual P, right? And then P of V minus P of V, what's this? This is just 0. So we just verify that P of V1 is 0. So meaning that V1 is nothing else but an element of the kernel of P, right? So that sits inside the kernel of P. And of course, well, we just finished with condition 1, right? Because we just expressed our vector V as a sum of two vectors. One is from the kernel, and another one is from the image here. That's it. Okay. So now let's look at the second property. Well, as for the second, we would like to check that the kernel of P, again, intersect the image of P is 0. Okay, well, let's just look at, suppose we have a vector, say V, which belongs to this intersection. Or maybe, well, we would like to use a different vector, so let's put a W. Intersect the image of P. Okay, then what does it mean? Well, it means that, look, I mean, well, in particular, it means that W belongs to the image of our projection, right? Of course, it belongs to both of them, but in particular to the image. But then look, I mean, you remember that the projection has this basic property that if you restrict it to the image, then this is the identity, right? A projection restricted to its image gives the identity. This property we proved last time. So meaning that if it just, right, so let me write it. So P restricted to the image of P is the identity. But the identity is injective. Indeed, it's just bijective. So in particular, it's injective, right? So injective. So the fact, well, let's just apply P to W. Look, W is in the image. So this property, yeah? So we have this property. So what is P of W? So P of W, it's the identity, so it's the same W, exactly, right? But on the other side, look, I mean, this W must be also in the kernel here, right here, at the same time. But what's the condition for being in the kernel? Well, it just means that this has to be 0, right? Because it's in the kernel. Yes, exactly. So now I'll just read it here like this. So it's 0 and then it's W. So W has to be 0. So if I take any element from the intersection, there's no way I can pick up something which is different from 0, right? So meaning that, I mean, what's the intersection? Well, the intersection is then the trivial, the 0 intersection. So the kernel of P intersect the image of P is 0. And this finishes the proof. This each vector from our vector space can be written as V is V1 plus V2 in a unique way. So here the key word is unique, because look, I mean, of course, if it's a direct sum, then the property that we can write V as a sum, it's already there, right? It's one of the conditions. So it's kind of tautological, automatic. So it's already noticed. But here, well, the crucial thing that we would like to say is that this is a unique expression. So whenever we have some other expression like this, then, so these two vectors, V1 and V2, well, they just have to be the same. They have to coincide, right? So basically, what we would like to show is that if V has a different expression like this one, say put V prime, V1 prime plus V2 prime, then V1 is the same as V prime and V2 is the same, has to be the same as V2 prime. That's what we'd like to show, right? Okay, good. So, well, let's just demonstrate this. Well, first of all, let's look at the zero vector. And how can we write it down? Well, of course, we can write it down as V minus V, right? Now, well, I can also write it down like this. So instead of the first copy of V, I put this expression. Yeah. So given, say, given presentation, and then I substitute my second copy of V by this one, V1 prime minus V2 prime. And well, what I'm going to do now, I'm going to reshuffle it a little bit. So I just write it down in this way, V1 minus V1 prime plus V2 minus V2 prime. Okay, shouldn't it be V2 prime? I think I'm fine. Okay, wait. Yeah, it should be. I think it's fine, right? Is that okay? Where, in which place? Yes, here's V2 prime. Yeah, basically what I just did, brackets, second equal here. V1 minus V2 prime, and then, well, this, sorry. Yeah, of course. That's a plus here, yes. It's a plus here, of course, yeah, because it's just this plus. Mm-hmm. And then look, I mean, I just take this and minus this. So it's just written here. Yeah. Okay. So, well, but then look, I mean, 0. So what do we see here? What do we see here? Well, we see that we can actually express this V1 minus V1 prime as, well, we can just also write it like this. It's minus 1 times V2 minus V2 prime. Yeah, we can just move this bracket on the left-hand side with minus. Okay. Well, then what do we see? Well, we see that this vector, right, is a multiple of this, right? And we all see that, well, this V2 prime sits where? It sits in V2 as well as V2, right? So this sits in V2. Yes? Because look, I mean, both of them, V2 and V2 prime, they're vectors from the second vector space, V2. Okay. So, but at the same time, if you look here, well, clearly, I mean, there's just a difference of vectors from V1, right? And it must be a gain in V1 because V1 is a vector space. So V1. So look, I mean, what do we see? Well, if we combine these two observations, we conclude that, look, I mean, this difference sits in both V1 and V2 at the same time, right? So let me write it, V1 minus V1 prime has to be in the intersection of V1 and V2. But then look, I mean, what we were given? We were given that V is a direct sum of V1 and V2. In particular, we also were given that V1 intersect V2 is 0. So meaning that, look here, well, it must be in the intersection, but right, in the intersection, there's only 0 in the intersection, so just 0. So there is no way, I mean, this difference, it has to be a 0 vector, right? So they must be equal. Yeah. Okay, good. So we basically check this condition. Now, what about this one? Well, we can argue in the same way. Well, let's look at this one. This is, well, we can just write it also like this. V2 minus V2 prime is also minus 1, of course, of V1 minus V1 prime. And then again, I mean, this has to be in V1. And the left-hand side has to be in V2 by the same reasons, by the similar reasons, right? And so again, I mean, this V2 minus V2 prime has to be in the intersection, which is trivial, which is 0. So that V2 minus V2 prime is 0, meaning that these two vectors also coincide. And this gives us the second equality. So, summarizing our arguments, we see that whenever we are given two expressions like this, it only can happen, well, basically we have only one expression, right? Because whenever we write it down like this, then it follows, it has to be that this V1 coincides with V1 prime and V2 coincides with V2 prime. So this expression is unique. And that's exactly what is written here. Okay, so that's a very useful fact. Again, whenever we have a direct sum, what it means? It means that we can write a vector V as a sum, but not just a sum, but it's a unique sum. You can express it as a unique sum of two vectors. Yeah, okay. Good, so now finally, so now again, suppose that we have a direct sum of two vector spaces. Well, then we claim that there is a unique linear operator, indeed a unique projection, P, such that the first vector space can be identified with the kernel of that operator, and the second vector space, V2, can be identified with the image of this operator. So in other words, if we combine it with the previous story, we can say that there is a sort of one-to-one correspondence between direct sums, right, and projections. So if we have a direct sum, we get a projection, unique projection, and if we have a projection, we get a direct sum. Okay. So, okay, let me just justify it. We have some minutes left to do this. So, right. So first of all, since we have a direct sum here, so since V is a direct sum of two subspaces, we can, of course, express any vector V, right, as a sum of two vectors, V1 and V2. So this is from capital V1, and the second one is from capital V2. And moreover, this expression is unique. Now we know this because it's a direct sum and we have just seen it before, right? It's a unique expression in a unique way. So, well, let's just define, because we would like to sort of to introduce certain projections. So let's just define it using the following formula. So P is a function, is a map, it's a linear transformation. Define, well, let's just look at the following linear transformation. Define a map P or function P from V to V by the following rule. So we just take, if we apply P to V, well, indeed we need to still to check that this is a linear transformation, and at the same time we need to verify that the kernel and the image of this P is what we want. So that's a V1 and V2. Okay. So, right. Okay, so well, let's just check that P is a linear transformation. But this is kind of easy because, we just need to apply the usual test, right? So whether some map is a linear transformation or not, so meaning that we have to check that it preserves the vector addition and the scalar multiplication. So this is comparably easy because, well, if you just apply it to the sum of two vectors, say V and V prime, then what's this? This is just the sum of the second, just the sum of second summands, right? Of the respective presentations, expressions. So let me write it in this way. Yeah. So of course, that's fine. So that's just P of V plus P of V prime. And the same story, the similar story holds for scalar multiplication. You know, if you just multiply this by scalar, the second summand also will be multiplied by scalar, the same scalar. So that's okay. Well, so P is a linear transformation. And well, also, I mean, well, clearly, what's the image of P then? Well, the image of P, right, consists of the second summand. Consists of the second summand. So it means that, well, it means precisely that the image of P consists of the second coordinates, right? But what are the second summands or second coordinates? Well, the second summands, they're precisely the vector space V2. Yeah. And well, what's a kernel? We're just looking, if you look for the kernel of P, what's this? It just consists of all vectors, right? It consists of all vectors such that if we apply P, we get 0 here. So basically it's just a subspace of all vectors where the second summand, the second component, this one, is 0, right? But this would mean that this V is just V1. So it means that the kernel, the subspace of all such vectors, is just the first component, the first vector space. Yeah. So that's it. So look, I mean, we have a linear transformation and the image is V2. It's a second component, second summand. And the kernel is precisely the first summand, the first component, which is V1. And this finishes the proof. So the proof is finished. Vn, right? Like we did with Rn, the same story. We just do it kind of inductively. Many times, repeated several times. Well, we can also repeat this kernel image fact several times. And in this case, we get the following observation is that whenever we have this direct sum, so it's the same as, to give projections, say P1, P2, and Pn, such that So first of all, those are projections, right? So meaning that they are, of course, all satisfies. If I compose each such projection with itself, I get pi, the same projection. And well, but okay, so well, let me just write it. So what are the conditions? If we just take, if we compose with itself two different projections, we must get a zero trivial map, trivial linear transformation. Yeah, so of course here I assume that if I is not J. Then, well, if I take the sum of all these functions, of all these projections, then I must get just the identity map transformation on V. And in this case, and so each VI will be just the image of PI. I from 1 to n. Yeah. So why this is a generalization of the previous fact? Why why this is an iteration of the previous fact? Well, because look, I mean, if it just n equals 2, that's precisely what we have had before. Then, so here's P1, P2, right? So V1 is the image of P1. V2 is the image of P2, good. Then take our P from the previous lemma, or to be just P2, okay? And then, well, it's very easy to see that, so, okay, so this is then fine. So V2 is the image of P. And why it's a kernel? Well, indeed, it's a nice exercise to see that indeed this image is nothing else but the image of, so let's put here the identity. The identity minus P2, which is P1, right? And that's exactly what we gain. Yeah, so we actually used it, right? This kind of, we use this formula because, well, look, I mean, we just took our V and we split it, right? This is V1. Yes, look, I mean, this is V1 and this is V2, right? So, well, if we add this, what it will give, well, we can also write it down like this. Look, I mean, I just put identity here and I put identity here. And what do we see? Well, we see that, so this is my P1 of V, and this is my, if you wish, P2 of V, right? And you see, if I add them, P1 of V plus P2 of V, I get the identity. Yes?